Okay, we've got the definitions here to finish up from section yesterday. So section 2.4, I think the very end, we really didn't discuss that at all. We did talk about some definitions. So these are a few definitions of things that we will need in our course. And then we'll try writing them as true biconditionals before we go into lesson 2.5. So a polygon is defined as a closed plane figure formed by 3 or more line segments. So as you look at the pictures that are polygons, they're all closed. They're formed by segments. And the segments don't connect unless they're just at the ends of it. 3 or more segments, otherwise it's not going to be closed. So let's look at the things that are not polygons and see if you can explain why these would be counterexamples to the definition. Why is this one a counterexample? It has a curve to it. Okay, how about this one?
It's not complete.
Yeah, we maybe would say it's not closed. These segments don't connect at the end of them. Right? How about this one? Now, when they're crossing like that, the segment does not connect the other segment only at the endpoints. They're connecting at a point that is somewhere in between. So, yeah, can't cross like that. This one? Not closed. How about the box? It's what? Not on the same plane. A closed plane figure. So it's supposed to be just flat instead of three-dimensional. Okay, so that's not a polygon. But what I want you to do is look at the wording in that definition. Can we write it as a true biconditional? How would you write that definition as a true biconditional statement? Try and grab a few new people today. Shay.
Figure is a polygon if it only
I think that was maybe exactly the words I had. A figure is a polygon if and only if it is a closed plane figure formed by 3 or more line segments. All right, so you will need to know that definition as we get into a later chapter. To build on that definition, a triangle is defined as a 3-sided polygon. A quadrilateral is a 4-sided polygon. So let's try again putting some definitions in biconditional words. Okay? Notice quadrilaterals, this one dips in. That really doesn't matter. It still has 4 sides. So as long as the sides are straight. Okay, so definitions are reversible. They're true in both directions. When we get to postulates and theorems, you can't automatically reverse a postulate and theorem. It's not always going to be true going in the reverse order. But definitions are that way. So let's try that triangle definition. We'll do this screen with your assigned partner and then the next one by yourself. So with your partner, come up with the definition of each of these as a true biconditional.
Figure is
Okay, have we done both of them? Got the second one done also? Decide who's going to speak from your group if I call them. Okay, Molly and Riley, how did you do the first one? Okay, did you do exactly the same? No? I had a figure is a triangle if and only if it is a polygon with 3 sides. I think I put the polygon in a different place than what you did. How about a right angle measures 90 degrees? How would you put that in a biconditional with if and then only if? Megan. And can I put your speaking document? Should have had you write it down. So she knew what you said. You wanna help her out, Abby? That's your
An angle is a right angle if one is
Okay, I guess, yeah, you guys would be in different groups, wouldn't you? Okay, angle is a right angle if and only if it measures 90 degrees. Correct. Okay, all right, now these two I want you individually to think. Raise your hand when you're ready to share. How would you do that definition? Zach? First one.
Figure is a quadrilateral if and only if it is four-sided.
Use the word polygon. It's a four-sided polygon. Because you could make a four-sided figure, but not close it up and that, so we need to have that in there. Okay, and how about number two? As a true biconditional.
What is this
An angle is a straight angle if and only if it's measured 100 degrees. Right, so definitions can be true biconditionals, which means you can use it both ways. All right, so that should have finished up the little part on 2.4. So 2.5 is the majority of our lesson today. We're going to talk about some properties, and then we're going to do step-by-step solving on some algebra problems and give the support for each step. So we're just adding something to what you did in Algebra 1, the support. And that's what part of geometry's task is, that you can get the reasoning support. We're going to be doing proof. Proof is an argument that uses logic, definitions, properties, and previously proven statements to show that a conclusion is true. Have you heard of previous geometry students talk about proof? Here's your beginning ideas on what proofs are.
They tend to
Just-
not like
They
proof.
tend to not like them. Well, you are going to be able to tell them, what did you think was so hard about that? Makes perfect sense to me. We hope, anyway.
Yeah, I get that.
Okay, what a proof is, as it says, it's a step-by-step argument. And today we're gonna just take a look at it in algebra, because when you did like that solving worksheet, I wanted you to show me your work, your step-by-step process. That's what we're gonna be doing today. We're just gonna say, what property did you use? Did you use the addition property? Did you use the multiplication property? Did you use the substitution property? You're just gonna give a name for each property as we go through. It's important that you give the justifications, because that's what's gonna help support the proof. A proof is a way that you prove a conjecture true. And if you don't have the supporting ideas there, then we don't have that it's supported. Yes, you need to have that justification. Can't be just because we want it to be, okay? So here's some of your properties. You've got a list there, and I think I put the properties in my own words also. Okay, the first four properties are like computational properties. And you did these in Algebra 1. Because it says addition property of equality, equal amounts can be added to each side of an equation, and the equation is still balanced. That's how I put it into words. Now, what I've got up here for an example in symbols maybe isn't showing exactly the way you would have done it in Algebra 1. So I'll let you write that down, and then we'll think, how did this look in Algebra 1? Notice what you're writing down is an if-then. So if you start with A and B being equal, then the first one says you can add a C to each side, and it's still going to be equal. What would that addition property look like if I put actual numbers? if 5 equals 5, then if I add 2 to each side, then I get that 7 equals 7. It's still true, isn't it? You know, in algebra, you probably would have had something like x minus 4 equals 10 was what you started with. And didn't you add 4 to each side of the equation? Okay, so add 4, add 4. You are doing the addition property of equality right now. And you end up with x equals 14. So what we're going to be doing today is we're going to say this is what was given, and we get this because we did the addition property of equality. We're just giving the justification. If it were a subtraction property example, I could change this just a little bit. Change that word. If this were addition to start with, you would have subtracted 4 from each side. So now to get x equals 6, you are doing the subtraction property of equality. Same with multiplication, where you would multiply on each side or divide each side. Now in the dividing, notice that it clarifies c cannot be 0. Why does it say that? Can you divide by 0? No, you can't. And if that doesn't make sense to you, let's take kind of a side idea here. 4 divided by 0, 4 divided by 0. So what number can you put up here that when you multiply by 0, you get 4? There's nothing that you could put up there, right? You can't do that at all. So why can you do 0 divided by 4? 0 divided by 4. Put something up here that multiplied by 4 gives you 0. 0. So that one works, the other one did not. So if you ever get mixed up, which one you can't do, see if you can put it into the long division to figure it out. Okay, understand those first 4 properties? Those are just some that you have used in algebra. Okay, the next group are reflexive property, symmetric property, and transitive property. These are still of equality, so we're still going to have equal signs in them. The reflexive property might seem kind of stupid. A equals A. Well, yes, something does always equal itself. We will need that situation in some problems because maybe we have a side of one triangle that's hooked on to another triangle, and so that same side is the side of both triangles, so we need to state that side for each figure. Is kind of why we would have that in there. So reflexive property is just something equal to itself. 7 equals 7. 5a equals 5a. That's what reflexive property is. Symmetric property of equality. What words did I put there for symmetric, Gary?
2 sides of the equation
Can be exchanged. So kind of switched. So notice the example, if a equals b, then b equals a. Just taking the 2 sides and switching it. Okay, what if I had a plus 4 equals 17? What would the symmetric property allow me to turn it into? John, what do you think?
Let's see, 4 equals 17, and 17 equals 4.
Symmetric property, take what's on the left and the right and just switch them. Someone else want to try it? Abby? 17 equals a plus 4. That is the example of symmetric. Okay? So you are just taking what's there and switching it to the other side. I wouldn't say flipping it, because if you say flipping, you might think that you could go 4 plus a. So whatever, to me that means pick it up and just move it. So you're not changing what it is, you are just switching the 2 sides of it. That's what symmetric property is. Now we will use that probably at the end of a problem. If we get that 5 equals x, I'm going to say if the x is on the right side, you haven't solved for x. you have solved for 5. So I want the x on the left side when you finish solving the problem. So if you have 5 equals x, to switch the sides, x equals 5 will be supported by the symmetric property of equality. That will be what allows us to switch the two sides. Okay? So some of you do that just automatically when you are solving. At least I saw that in some of your work on that worksheet. Okay? When you're giving the step-by-step, you have to explain that's using the symmetric property. Oops, I didn't want to show that last one yet. Transitive property has more parts to it. I think of transitive in my mind as a train where things are hooked together. Okay? So we've got one equation, and then we've got another equation in the hypothesis. What has to be true about those two is the right side of this equation has to repeat as the left side of another equation. That hooks the two equations together. And so in the end, we would know the first thing, A, is going to equal the last thing, C. So to put that together as a little bit longer example, if x plus 4 equals 7, and what do I need to say next? 7 equals 8 minus 1, then x plus 4 equals 8 minus 1. X plus 4 equals 8 minus 1. This was the left, this was the right. The middle part drops out, it hooks them together, hooks the ideas together, but is not there anymore. Notice that these two things are equal, and they were the ones that we didn't know equal before. So how's that a train? Here's the engine, here's the train cars that are hooking together, and here's the caboose. So the engine and the caboose end up hooked together in the end. You could have multiple things in the middle there if we want to make it a little bit more complex. And the last one was substitution property. What's a substitute teacher? A teacher that's here in the place of the original teacher. Substitute. You're putting something in for what was there originally. So if A and B are equal, then B can be substituted for A in any expression. You did that on algebra problems like it said, figure what x plus 5 is when x equals 10. So it's telling you the value for the variable to put in and then compute through. So that's the type of substitution you have done. Okay, got the notes? A reminder, I think I put distributive property. Remember what that one looks like from algebra? A times some quantity, either addition or subtraction, so there's more than one term. And that's going to be A times B plus A times C. As you give support in some of the problems today, you might need to refer to the distributive property. And you might also refer that you combined like terms. Combining like terms is not doing something on each side of an equation. It's just on one side or the other. You're just simplifying. So there are times we'll say, we just simplify. And mentioning maybe combining like terms or adding together. Those might be some words that we would use to help clarify the simplifying. All right, ready to try some? All right, so here's what you would be asked to do. Prove how to solve this equation. Write a justification for each step. Now I've kind of set this up in a little table. I'm going to do the math on the left side. I'm going to put the reasons on the right side, or the justification on the right side. You probably want some in your notes. So yeah, it's up to you, but I'm sure you will want some examples in your notes. Okay, now the first step, we have to get all the thinking into this bottom part. Okay? So typically the first step is you're going to bring whatever equation you're solving into the solving area. So I'm going to put that equation, and it was given. It was right there in the problem. It said solve this. All right, just your algebra, what would be the step that you would do? Add 8 to each side or simplifying on one side? Each side, so what property are you using? Okay, so the next thing's gonna be supported by addition property of equality. And for these first ones, I'm gonna show the work, just to make sure everybody's with me. Okay, so we get 4m equals -4, addition property of equality. There is no addition property of congruence, because have you ever solved a problem with a congruent symbol in it? No, we don't use congruent when we're calculating. So it's a property of equality. Okay, and next step, divide each side by 4. And some of you might say that's multiplying by the reciprocal. So sometimes it could be a different property. I think I did division property. And we get m equals -1. You might be more likely to do multiplication if it was like 2/3 x equals 10. Okay, there's your first proof. Just doing the solving, just find each step. What did they think was too hard? Yeah.
Like
On the
when we have
homework-
to write given equation and
Yes.
add addition property.
Right.
We'll have to show that
So
one.
this type of thing, and I'll probably allow you not to have to show that +8 divided by 4 divided by 4. If you didn't have those, but you still had the steps, the
Right.
reasons, I would count that, right? Okay, because you need to explain where each of these things comes from. So where did this come from? It was given. And given, it has to be there exactly. If you're creating something, it's not given. All right, let's try another one. Got the back side of papers. Prove how to solve this one. It's not a real long one. What would be the steps to justify solving this? Multiply this, so you can divide by it, and multiply by 2. Yeah. Divide by fraction, but if not, let's multiply by the reciprocal instead. Let's multiply by. Okay, how many steps? Practice the original test. You're multiplying by the same thing on each side. So it's just multiplication property. How many did a multiplication property? Anyone do a division property? They could divide by 1/2 on each side. Okay, how many reasons do you have? Got 2? The given, and then the multiplication property of equality. Just like that? Have it.
So you don't have to put anything isn't the answer.
Nope. When it says T equals, we would know that that's the answer. Okay. What is the temperature in degrees Fahrenheit when it is 15 degrees Celsius? We're going to use that equation and justify each step. So we're not really solving it for like X or something like that, but we are coming up with what the temperature in Fahrenheit is. So I guess we're solving it for F eventually. Okay, what do you think the first step would be? Get the given equation in there. Okay. The given equation. This could be done more than one way. Let's see if your ideas match up with what I did. Ideas.
Plug in 15%.
said plug in, what's the actual word we would use? Okay, we're doing the substitution property of equality. Okay? Substitution property of equality, don't do any calculating, just show so that whoever's following this can see what you substituted. Now we just need to do some simplifying, right? We just need to multiply this. So we're gonna simplify by multiplying. And then we're just gonna simplify by adding or combining like terms. So the end of that is a little bit different because we're not doing something on both sides of the equation. We're just simplifying that one side. So to answer the question, 59 degrees Fahrenheit. You don't have to put combining like terms. If you put simplify, that should be good enough, but I just thought I would put it there, and it's sure helpful to put it there. It would help someone trying to follow if you wrote it. Okay, question on the idea there. I'm gonna have you do one kind of like that. See if you're done writing. Okay. One that's kind of like that, but I changed it up a bit. Go through, justifying each step. You're doing a whole bunch at one time. You need to break that down into steps. Before you can put that number in, you have to have the given equation there. This one probably has some variety to it. We'll see if we get the same answer in the end, and if you've justified your steps. How many lines do you have with support? You got a couple?
I
So
got,
three
so far I got 3.
And you're doing one more, so you're gonna end up with 4, it looks like?
Yeah, that's what I
4 steps?
got. Figure out how to
It
do
could be
this.
done differently, even your way, Kenneth, it was 4 you were getting. Okay, Kenneth started out distributing after he had the given equation. Anyone else do that way? How many used distributive somewhere? You didn't have to. Right, I don't think I did distributive property. I did the given equation, I substituted in, then I simplified the parentheses and simplified by just multiplying. So the answer there in the end was 30 degrees Celsius. Thumbs up or down if you feel that you knew how to do that one. Okay. The reasons that we're doing right now probably is kind of tied into that worksheet that we did where we solved equations. you struggled on doing that, you're probably kind of iffy here as far as what to do at times. Okay, now we're gonna start with a geometry idea. Okay, like algebra, geometry also uses numbers, variables, and operations. For example, segment lengths and angle measures, they're actually numbers. You can use these same properties of equality to write algebraic proofs in geometry. So on these, I think I have maybe 2 examples. We're going to start with a geometry idea and then convert it into the algebra equations. Geometry ideas, we might need our chapter 1 notes. That's chapter 1 notes, Sandy? Pull that out. Chapter 1 notes. Recognize this kind of a problem from the first chapter. Okay, but we're going to work it by giving all the steps along the way. Now, it's a geometry type problem, so we're going to start with a geometric relationship that's true, which you probably didn't do in chapter 1. I want you to look up the segment addition postulate, because that's the idea that we start with in this group. That's the segment addition postulate. If you remember it, wonderful. If not, at least let's look it up and see. Got something about it for me, Paige? Okay, so it's something with one point being between 2 others, and then you're saying the small segment lengths, those measures add together to give you the whole thing. Now, if you want it to match up exactly with what I'm showing, I started with the whole thing. The whole length of NO, that distance, is equal to the distance, I showed too much there. Just one more thing. Okay. The distance from N to M and M to O. As you look at this, that reminds you, algebra or the segment addition postulate. Okay, so that's the geometry behind what we're going to do. Okay, that's what supports that we can add these segments together. Now we can substitute. Substitution property of equality. What can I substitute for NO? 4x minus 4. What can I substitute for NM? 2x. What can I substitute for MO? 3x minus 9. So put those in there. Now it's an algebra problem. It's not a given equation. It's one that we created based upon the geometry that we started with. Now do your solving. Justify each step. Are you doing a property or a simplification? Depends if you're on one side or both sides. This could go different ways. Oh, I think I just put the parentheses to show you that that's the whole thing I put for now. Are they important when it's addition? No, they really don't have to be there. If you're stuck, how about combine like terms? On the right-hand side, I see two things with X's. If the parentheses are screwing you up, they really don't have to be there because it's just addition. Yeah, you only want to do one thing per line, okay? Because if you are needing to give more than one reason, you've done more than one step. So break it down step by step so that it can be followed. Will you ever need the parentheses? You would especially need them if I had to like take 2 times that so that I would distribute. If it were subtraction, it would make a difference because we have to subtract both parts. Addition would be the only time. If it's just a simple addition, you wouldn't need those because you're not doing anything else to it. Okay? Right, hand your solution to your partner. Have them look through it and see. And if they need help, yeah, I think I did do front to
I don't
back.
even know, it's really good.
I know. Front to back, I think.
I don't have one, I don't get it.
You can
You
go.
walk me through what you did. Wow. Oh, right.
Did a little more when I was going through here, so I wrote it step by step.
Now, what I don't see anywhere is the justification. What properties did you use? Where did you simplify? We need to have that right-hand side, those words, that needs to be there. Okay? So I don't know if Tristan can help you come up with what those are.
I know
Now
what
we're
it is.
gonna
You have to write them down. Okay. And I think you should have one more step because you haven't solved for X, you solved for 5. How do you switch it
What's the
to?
whole street back?
What property said you could switch to 2 sides?
He was awesome. Him and Miss Oxford's little feud that they had was hilarious. Nobody thought they
There's
were
one
gonna
that
get
says you
married.
can switch the sides.
I'm never gonna call
The 2 sides can be
Miss
exchanged.
Oxford. Just like Miss.
It's hard for me to
I still call Miss Busy Miss Oxford.
Okay, here was my attempt. Did they end up with the X on the left side? If not, they didn't solve the equation for X. They needed maybe that symmetric at the end to get it to say X equals 5.
So there's gonna be like a lot of answers for this.
Well, yes. I mean, in the end, we should get the same solution, but what steps they go through could be different. And that's why I wanted you to look at somebody else's. It could be different. Yes.
A couple
A little
years.
bit longer. You know, am I gonna read through every possibility? No. What I will probably do is show you one, and then you use some math knowledge to figure out if what they did was another version that's okay.
I don't.
A lot. Okay, let's justify this one. Start with the geometry idea. But it actually wasn't good. There wasn't good. Okay, now what is the geometry that we would use to begin this one? Because there's no given equation right here. There's some geometry that you need to start with.
Alright.
Is it gonna be segment addition postulate? Angle addition postulate is this one. It could be that it's definition of a midpoint. Could be that it's definition of an angle bisector. I just did a couple where we did angle addition postulate. Okay? We're kind of running out of time, so let's at least get a start on this one. What would the angle addition postulate statement look like? E2 chapter 1 notes would be a place to look. Measure what angle equals measure what angle plus measure what angle. The M and the angle sign. Yes. No. use the ones in the diagram. Okay, you use the angles that are in the diagram. There's the way I wrote it. Measure of angle ABC, the big one, is what I started with. It's equal to the measure of angle ABD plus the measure of angle DBC. Yes, it's the measures that you're adding together. The M goes before the angle because that's what you measure, yes. Yeah, it could still be done that way. Right, if it were completely flipped around, that's still possible. Okay, what will we probably do after that? Substitute, and then I'm just gonna click through this one. I think you're getting the idea. I combined like terms, I think. And then I subtracted the 9x from each side, and I needed to divide by -1. I don't have to do a symmetric because the way I set it up, my variable ends up on the left. Okay, just looking through that one, question? All right, now if you flip the page, you'll probably see there's a reflexive, symmetric, and transitive of congruence also. You can't use those when you're calculating, but there is such a property.
You wanna use those?
So, yes, you're going to be given some examples of properties and you're gonna name it. So we'll quickly look at one set of examples. So these are still something congruent to itself. Symmetric. If you have two things congruent, you can switch the sides that they're on to make a new statement. The transitive, remember how you have to have the repeated part that hooks it together? What's the repeated idea here, or fact? Segment RS. That's your connecting idea. So you won't really use these in the solving, but for these examples, they're going to simply give you a statement and say, which property is this? It might be reflexive of congruence, it might be reflexive of equality. So you have to tell me the property, reflexive, symmetric, or transitive, and then is it of equality or of congruence? Okay, one set of problems looking like this are on that. So this is the type that it will say. Okay, so identify the property that justifies it. If it says angle QRS is congruent to angle QRS, if the property of congruence, which one? Reflexive. So that's reflexive property of congruence. Okay, the next one, I didn't really put if and then, but it still means the same thing. Measure of angle 1 equals measure of angle 2, so measure of angle 2 equals measure of angle 1. Symmetric property of equality. How about the next one? It's a property of congruence, which one? Okay. This is the transitive property of congruence. Yes. And the last one? Okay. It's a property of equality, because it has an equal sign this time. Reflexive. So for those, you're going to be picking out which one it is. Okay. All right, we kind of used up our time there. Page 107. 1 through 11, I'm going to give you the odds on that part, so you can double check if you're doing it right. And remember, there could be more than one way to do it, so you might not have exactly what the book has, but you're probably pretty close. And I'm going to give you a terms and concepts worksheet that will be due next week, but I think I'll give it to you today unless you want to wait. You want to wait till you have more homework? Okay.
Oh, we got plenty of homework now.
I'll try and put it in e-backpack.
Oh, that'd be good.
I do have a paper copy.
Print that off.
I think I'm gonna hand it out today anyway for want to get a start on it.
That's needed publicly. If they could, you know.
We'll discuss this worksheet on our review day, which is Tuesday next week. But you can start matching up yep, you can start matching it up. Why don't you hand some back?
Oh.
That's what you
Yeah,
want.
like, cause the bells help ring, and I don't think nobody got time for that.
Tuesday. So due next Tuesday, which would be January 27, I think. So that's kind of a ongoing, but you could probably get work on part of it based on what we did. We haven't covered everything yet, but we did quite a bit of it.